Physics relies on internationally accepted reference standards. These basic, arbitrarily chosen units ensure that a measurement taken in one country remains perfectly accurate in another. Even with these standards, no measurement is perfect. Every instrument reaches a mechanical limit, leaving us with uncertain digits that we can only estimate. To maintain scientific standards, we must drop these uncertain digits. Reporting them suggests a level of precision our tools didn't actually provide. Rounding sounds like a simple grade school exercise, but relying on basic math instincts risks introducing errors that can impact massive scientific datasets. Mastering these specific rounding conventions provides a necessary defense for the integrity of experimental data. We can test this using 4 textbook examples: 2.746, 1.743, 2.745, and 2.735. We need to round each to 3 significant figures. Most arrive in the lab with a primary school rule in mind. If the final digit is 5 or higher, you automatically round up. In the context of a high-volume physics experiment, applying this single rule to every measurement unexpectedly changes the behavior of the entire dataset. To prevent errors, physics employs a strict convention for dropping digits that overrides standard math habits. We'll start with the 2 cases where our common rules still apply perfectly. Rule 1. If the insignificant digit is greater than 5, the preceding digit is raised by 1. The 6 drops, the 4 becomes a 5, resulting in 2.75. Rule 2. If it is less than 5, it remains unchanged. The 3 drops, leaving 1.74. These baseline rules are logical because the numbers are objectively closer to their next whole interval. This logic works until a measurement sits exactly in the middle of 2 options, creating a mathematical paradox. This brings us to the edge cases, where the digit we are dropping is exactly 5. In this scenario, the decision relies entirely on whether the preceding digit is even or odd. Under the even digit rule, if the preceding digit is even, the 5 drops and the number remains unchanged. 2.745 becomes 2.74. However, if the preceding digit is odd, the 5 drops and the digit is raised by 1. 2.735 also rounds to 2.74. Following these strict rules means that 2 different starting measurements, 2.745 and 2.735, correctly round to the exact same value. It's natural to wonder why we use such a seemingly overcomplicated rule for a single number. Consistently rounding up on 5 across thousands of data points creates an artificial upward inflation. This chart shows how that bias warps the final results of an entire experiment. The even-odd rule is a statistical tool. By pulling roughly half the numbers up and keeping the other half down, the micro-errors cancel each other out over large sets. This convention acts as a statistical equalizer, ensuring that large-scale experimental data remains balanced and objective. Even when you know the rules, applying them too early in a problem can still ruin your final calculation. In intermediate steps, you must retain at least 1 extra insignificant digit during all arithmetic operations. Rounding to the proper significant figures should only occur at the absolute end of the problem to prevent small errors from compounding. To keep it straight on exam day, remember, 5 after even, stay. 5 after odd, rise. These rules aren't just arbitrary hurdles. They are the fundamental grammar used to maintain the technical accuracy of scientific measurement.